Hi, welcome to part 3 of 3 for 1.1 functions, domain, and range. This is our last video for this lesson. In this video, we're going to be looking at number systems to start off with, and then we will be focusing on domain and range for relations or for functions, and we're going to be doing this just by looking at their equations. Okay, so I've given you a bunch of equations in this handout. Some of them are new, and so we'll take our time going through those, but we're going to learn how to determine the domain and range by looking at those equations. All right, first off, let's talk about number systems. Okay, so in this course, we're going to be focusing on real numbers, which is actually a collection of many different types of number systems. Okay, I'm going to start off with the very inside. The first number system that was created by man or discovered by man are the natural numbers, and those are just simple counting numbers like 1, 2, 3, 4, 5, etc. Finally, one day someone said, hey, you know what? I think 0 should be included in that number system as well. So a new number system was then created, and it consists of all the natural numbers plus the number 0. So if you're working with the whole number system, you would include 0 and the natural numbers 1, 2, and 3. These number systems are given symbols. The natural number system is given the symbol n, or the letter n, to denote that system. Whole numbers is given the symbol or letter w. Okay, it makes sense. And now moving on to integers. So integers, this system is denoted by z, the letter z. Integers are just like whole numbers, except it includes their opposites. So it includes all the natural numbers, whole numbers, and all their opposites, like -1, -2, -3, etc. Okay, and the integers, these are still considered whole numbers, so we don't see -1.5 or a -5.1. They have to be whole numbers. Okay. Now, outside of that, we have the rational number system, which is denoted by the letter Q. So Q is our symbol, basically, for rational number systems. And rational numbers represent any number that can be written as a fraction. So, for instance, -9/2, that can be written as a fraction. Now, it also includes decimal numbers that keep repeating. So that little line there means it keeps repeating 1, 2, 1, 2 afterwards. We also have decimal numbers that do terminate, like 11.23, that can be written as a fraction. And we got numbers like 3/4 as well. Okay. So what I do want to mention is that this number 7.12, this fraction keeps repeating forever and ever, right? Whereas some of these actually terminate. Okay. So either way, they're both part of the rational number system. So outside of all these is another system for numbers, which doesn't include any of these other ones that are here. And it's quite separate. And the irrational numbers are given the symbol I. Okay, that is an I there. And these numbers are basically decimal numbers that that do not terminate or repeat. Okay, so I'll add that in here. Numbers that do not terminate or repeat. Okay, examples of those are like the number pi. Okay, if you know, people always try to, you know, claim how many digits of pi they know. Well, really, the number pi continues on and on forever. It starts with 3.14, and the digits just keep going, and it actually never ends. That's also the case with the square root of 2. Okay, you could put the square root of 2 in your calculator, and you would see that that also doesn't terminate as well. So I'll just do this quickly for an example, the square root of 2. And we can see here we get so many decimals And that actually decimal number continues on and on. All right, so now all these numbers, it took a while for us humans to come up with all these different number systems. And there is one group of number systems that actually includes all of these, and you might have guessed it, it is the real numbers. So the real number system, it's given the symbol R, and it includes all of these, both irrational and rational numbers. Okay. Now in math class, when we're doing graphs and working with the equations, and we're working with the Cartesian plane, the XY axis, the Cartesian plane is actually using the real number system. So every single number that exists on that number line is part of the real numbers. All right. So let's kind of move into the lesson now. So to determine the domain and range of a relation, when only the equation is given, one must analyze the allowable values. Okay, so when you're given an equation and you're trying to figure out the domain and range, the domain is all the values of x that are allowed to go into this function. Okay, and we want to write the set of all those numbers. So there are many different numbers that can go into x in this equation. So we don't want to write them out like we did in the previous video. So we have another notation that is pretty common when we're working with the equations. Okay, and you would have seen this last year in your previous math course, but to the domain for this linear equation, I know this is linear because there's no, the exponent is just 1 on the x, okay, so this is in the slope y-intercept form. So with linear equations, I'm really allowed to put anything I want in for x. Okay, you could give me any number that you can think of, and I can plug it in for x, and I can give you the corresponding y value. And what's also cool is that every value that goes in for x gives you a unique y value out. Okay, that means it is a function. So how can I write down this list of all these x values that are allowed in this function? Well, we first got to state the number system. Okay, so we're going to say that all my values of x are elements of, so it's this funny looking e, okay, it's called epsilon, and it's part of the Greek alphabet. So x is an element of the real numbers. Okay, and if there were any restrictions or anything, I would state that next, but there aren't, so then I'm just going to close the bracket. Okay, so what this means is, I'm going to kind of spell this out here. The curly braces that you see here, it means that this is a set. Okay, so there's a set of values of x. So this e here means element of, and the r means real numbers. Okay, and obviously the d stands for domain. So when I put this all together, I got the domain is the set of all the x values that are elements of the real number system. Okay, so basically this means every number that exists in the real number system can be used for x for this equation. All right, the domain is kind of similar to this. So we will write that off over here. Or sorry, the range, we'll do the range next. Now the range has to do with all the output values for this function. So this linear graph, I know it's going to extend to positive and negative infinity. Every value of y is going to be used. So I can say, I open up my curly brace, which basically says the range is a set. Okay, so the y values are going to be a set or an element of all the real numbers. And let me close the brace bracket. So you might be a little bit uncomfortable writing this, drawing these brackets using this symbol, but what this means is it basically says y is every number that exists in this pool of numbers. All the rational numbers and all the irrational numbers. Every number that exists is part of it. Okay, so we have the domain and range defined. That's beautiful. Let's do a quick graph and see if it kind of matches what we know about this. So before I do the graph, I want to figure out my slope for the equation. So that is my m value for the equation of the line. So the slope is 2. And this here is my y-intercept. That's my b value, right? So the y-intercept is -5. So that's great. I got a y-intercept of -5 and a slope of 2. I can easily draw this. I'm going to put my y-axis right here. I think I need to get a new pen. This keeps happening. Okay. All right. So there's my y-axis, and then the x-axis can go right. We'll put it up here because my y-intercept is -5. So I got -1, -2, -3, -4, -5. So that's my first point for this line. And then I have a slope of 2. So remember, the slope is my rise over run. So it just means I gotta, from this point, I gotta go up 2 and over 1. That would be right here. All right, so now I'm just gonna draw a nice straight line going through. And I'm gonna label the equation y equals 2x minus 5. Okay, make sure the axes are labeled. Make sure the graph is labeled. I got my y-intercept shown. So this is perfect. So how does this confirm my domain and range? Well, I can see that this graph is going to keep going up to infinity and to negative infinity for both x and for both y. So that tells me that all the values of x are going to be used and all the values of y are going to be used. If there were any restrictions, I would then try to include that somewhere before that final brace bracket is mentioned. I would try to put that, any exceptions or any restrictions. Okay, let's move on to the next graph. All right, so this is a quadratic. Okay, and it's actually in vertex form. Okay, so I'm kind of going to review some quadratics right now. So it's in vertex form, which looks like y equals a x minus h squared plus k. And this is called vertex form for a reason, because it gives us the vertex. The vertex would be hk. Remember, this x value for the vertex is always the opposite of what it looks like in the bracket. And as we go over transformations, we'll see why that actually looks like that. So in our example, this means that my vertex would look like 1, 3. Okay. So I'm going to do my best to draw a sketch first for this, and then we will answer the domain and range part. So there's the vertex. And I also know, depending on the value of a right here, it lets me know if this parabola opens up or down. Okay, so if a is greater than 0, this opens up. Okay, and if a is less than 0, it opens down. So in our equation, I can see there's a positive 1 here. So we'll write that in. A equals 1, therefore opens up. Okay, so I'm going to have a nice parabola that's going to open upwards with a vertex at 1, 3. That will be enough for me to do the domain and range. So here we go. I'm just going to draw my axes going through here. There's the y-axis. And here is the x-axis. Okay, this vertex is at 1, 3, so that would be right here. There is 1 and there is 3. Okay, and this quadratic, because a is 1, I know what it's going to open up. And I also know that there's been no stretches or compressions that have been applied to this. So it's going to look like my basic parabola shape. So I'm going to have points 1 to the left and 1 up. Same with 1 to the right and 1 up, like the standard y equals x squared. And the next one would be 2 to the right and 4 up. And the other one is 2 to the left, 4 up. Okay, we'll go over this a little bit more, how I knew that looked like that, but maybe you might remember from grade 10 also. Okay, just going to label the graph y equals x minus 1 squared plus 3. Okay, so just going to clean this up a little bit. Okay. All right. So now for the domain and range part. So the domain, I want to list all the x values that are used for this parabola. Okay, so this parabola is going to keep going upwards. It's going to use all these x values this way. And it's also extending out this way. So it's going to use all the values of x that way. There aren't any x values that are not allowed to go into this. So we can see that in the graph. And we can also tell by the equation. There's no reason I can't put any number in there and make a calculation and get a specific y value out. So just like all quadratics, our domain is just x is an element of R. Okay, this is actually true for all quadratics. Now the range, on the other hand, is a bit different. Okay, so the range, oops. Okay, y is also an element of the real number system, but we're not just getting any y value out. So when I look at the graph here, I can see the smallest value for y. The smallest value for y is right here at 3. And it actually includes 3. And then from there on, it uses every value going upwards. So I basically know that for this function, the y values are going to be from 3 and up. So I can state that in here using an inequality interval. So I'm going to say that y is greater than or equal to 3. Okay, let me make that 3 a little nicer. Okay. So this tells me y is greater than or equal to 3, which is what we have here in the graph. Okay, let's move on to the next one. So this next equation is going to be a new one for you guys. I'm going to do a couple things just to help us to get the domain and range. But as far as the graph goes, I'm just going to pull it up on Desmos so that we can take a look at it. Okay, I will be getting to these later on in another lesson when we go to use them a little bit more predominantly, and we'll make sure that we learn how to draw them at that point. So the same actually goes for this one too. Okay, so for C, this is called a rational. It's called a rational function. Okay, and remember the word rational just means anything that can be put into a fraction form. So here are our polynomials in a fraction form because we have 1 over our binomial. So there's a couple things that we have to consider when we're looking at this. I'm going to bring up Desmos first. And I'm sure you guys have seen this before probably, and it's kind of one of those weird things in math. And it's weird, but it also makes sense. And it's the fact that you can never divide something by 0. Okay. So like for instance, the number 1, if I try to divide it by 0, I get undefined. Okay, it's actually something that doesn't exist in math. You can't take a number and divide it by 0. It's kind of like saying, okay, I'm going to take a chocolate bar and I'm going to chop it up into pieces that are as big as 0, and I want to know how many pieces I'm going to get. Okay, so you can't chop up a chocolate bar into pieces that are of 0 size and then try to count them all afterwards. Okay, it doesn't make any sense. That's why it is undefined. So in math, we can never have division by 0. So I'm just going to write that out first. Division by 0 is a big no-no in math. It is not allowed. Okay, we say it's undefined. Okay, because it can't be determined. So why am I bringing this up? Well, if you look at our equation, we have 1 divided by x plus 3. So I have to be careful here. I got to make sure that this is never equal to 0. I can't have that happen because then we would have 1 divided by 0. Okay. So I want you to think for a second, what number would make this 0? Okay. So if I put 0 into x, I'm going to have 0 plus 3. That would not be 0. What would x need to be so that when I do the sum of those two, I get 0? So you might have guessed it, and we know that x cannot be 3. Okay, so I'm going to say here the expression in the denominator, okay, cannot equal 0. Okay. Therefore, x cannot equal negative 3. Okay, why did I say negative 3? Well, if you plug negative 3 in for x, you're going to have negative 3 plus 3. Well, that gives you 0. And that would be like trying to do 1 divided by 0. It is undefined. It is not allowed. So the fact that x can't be negative 3, that's a restriction. Okay, that tells me that on my graph, I'm going to start to draw this. Wow, I almost had that perfect. Okay, do it one more time. I guess I'm not going to be too picky this time. All right, so there's our y-axis, and then here is our x-axis. Okay, we know that x cannot be 3, negative 3. So negative 3 is right here. This means that this part of the graph is not allowed. There cannot be any part of this function, cannot be anywhere along this dotted line. Okay, we call this dotted line, it has a special name, and it is called the vertical asymptote. So the line x equal to negative 3 on the graph is called a vertical, a vertical asymptote. Okay. This vertical asymptote is this line right here that I've drawn. Okay. It's basically a boundary line. So it doesn't show up like in the graph. So if I put this equation in Desmos, you're not going to see that boundary line unless the settings are turned on to show it. But most likely you won't see it, even if you're using your graphing calculator at home. Okay. Now there's one other thing that's special about this too. So the function actually has another asymptote. Okay, and maybe you're thinking, well, what could be the other asymptote? Well, it has to do with the fact that this is rational. It has to do with the fact that we have 1 divided by something. I'm saying something because x is down here. We can put anything we want in for x except for -3. That's not allowed. So by putting numbers in here, I always have 1 divided by something. Okay. Now 1 divided by something can never equal 0. Okay. You can give me any number you want for me to plug into x. And when I do 1 divided by x plus 3, I will never get 0. Okay, so let's just write that out here. Okay, so we can say all the values for x will never generate a y value of 0. Okay, so just to demonstrate this a little bit here, so if I do 1 divided by, okay, I'm going to pick a number for x. I'll go with 50. I'll write 50 plus 3. Notice I don't get 0. I get a small number, but I don't get 0. Okay, let's make this a bit bigger. I'll make x 500. Okay, so what I'm doing is I'm plugging in numbers for x, right? So I made x 500. I end up getting something even smaller, 0.00198. What if I make this negative and maybe make it like 50,000? Will I get 0? No. I just got a negative number this time, and it's really small, 0.00002. Okay, but it's not 0. The bigger this number becomes for x, so the more extreme it gets, what happens is this function starts to get really, really small. This negative 2.00012 times 10 to the negative 9, this means this decimal needs to move over 9 to the left. This is a really tiny number. It's 0.9 zeros and then a 2. So is it small? Yes. Is it 0? No. It is far from being 0. Okay. I can even increase this, and notice we'll never ever get 0. That's what's special about this function. Okay, 1 divided by a number can never equal 0. So let's close this off for a second. I'm going to draw the second one. Okay, and I'm going to draw it right. I'm going to change the color. So this is actually called a horizontal asymptote this time, and it's along the x-axis when y is equal to 0. So just to get back to this a bit, the function has another asymptote. All the values for x will never generate a y value of 0. Okay. So the line y equal to 0 is the horizontal asymptote. Okay, and I'm highlighting that in pink because it's the pink line on the graph. Okay, so what I've done here is I've actually have not drawn anything for this yet. I've only shown what it can't be. Okay, so x can't be along here at -3, and y can't be along here at 0. Let's go ahead, let's state our domain and range. So the domain for this is x is an element of the real numbers. We always write that. And now we're just going to say what, I put this line through here, okay? And now I'm going to state the restriction. Okay, we're just going to say that x is not allowed to be -3. Okay? We can use anything else, and that's fine. And when we use all those other numbers, what happens is our range, which is an element of the real numbers, can be anything else too, except we will never get 0 from this. So we will write here y cannot equal 0. Okay. So again, to go over this, that domain and range, it basically says for my x, you can pick anything to go into here. Anything is allowed except -3. And in doing so, the result of that, my y values that are going to come out can be anything except 0. Why can't they be 0? Well, 1 divided by something can never equal 0. Okay, if you can come up with something where 1 divided by a number gives you 0, then go ahead and let me know, but I know it does not exist. Okay, right. And before we go further, I do just want to mention that these kind of functions, for right now, we're going to just look them up on a graphing calculator. So I'm going to go ahead, I'm going to put this in Desmos, and we will see what the actual graph looks like. So our equation is y equal to, and entering in this, be very careful. It's 1 divided by x plus 3, so make sure you use a bracket in the denominator. Okay, if you don't use the brackets, you'll be graphing something different. All right, so here it is, this famous looking graph. Okay, you can see at -3, the graph doesn't ever cross. As I zoom out, you can see it gets closer and closer, but it never crosses. Okay. You can also see like the graph never ever equals 0. Okay, I'm going to zoom out. I'm going to try to zoom out pretty far. And then I'm going to zoom in this way. And you can see as I zoom in more and more, the graph is still above the x-axis. Okay, so it has never crossed. All right, now just to zoom out a bit. Okay, we're almost there. Okay. So that is our graph. It is kind of funny looking. We basically say it has 2 branches to it. They're both on either side of the asymptote. So I'm just going to transfer this over for now. And I'll do this in red. So we kind of got, when we draw this, we want to make sure we're hugging the x-axis. We don't want to cross or touch it. We just want to get close. And same thing with the vertical asymptote. Okay, make sure you put your arrows on it to show that it keeps continuing. And same with on this side. Okay, I know this is a weird looking graph, and I promise you guys, as we progress in the course, you will learn how to draw these. And I'm going to explain why it kind of has this shape along here and here. And we'll look into it a little bit deeper. For now, because we're doing domain and range, we want to figure out what values of x or y are restricted. Okay, and those are the VAs and the HAs. Okay, and moving on to this one here, y equals root x minus 1 plus 3. Okay, so before I graph this, I want to think about what am I allowed to put in for x? Okay, what kind of values are allowed? Can I put anything into this square root right here? Okay, and you might think, yeah, you could put anything you want in there. Well, can we take the square root of a negative number? I don't think we can. Okay, so in fact, I know we can't, and you might know that too as well. So the square root, let's say, of 4, we know is 2. Well, what if we put -4 in? We get undefined. Okay, so there's a good reason why it's undefined, and it's because uh, the square root of 4 is 2, because 2 times 2 gives us 4. The square root of -4 would have to have 2 numbers that multiply together to give -4, and those numbers have to be the same. So there's no 2 same numbers that multiply together to give you a negative. Okay, -2 times -2 is +4, not -4. So we cannot take the square root of any negative numbers. Okay, just to show another one, -100, also undefined, doesn't work. What about 0? Is 0 allowed? Oops. Is 0 allowed? Yeah, we just get 0. Okay, I know I said that like it was a surprise, but I already knew that. So um, okay, so that means we need to be a little bit careful here. We don't want to put anything in for x that's going to make the result of this negative. That would be undefined. It would not be allowed. Okay, so we will say here going to erase this to give me a little more space. The expression under the radical, that's the square root sign, okay, must be greater than or equal to 0. Okay, if we don't follow that, we will have undefined. Okay, so basically what I'm saying here is that the square root of x minus 1, actually let's get rid of the root part. Just the expression under the radical, the x minus 1, so that needs to be greater than or equal to 0. Okay, well what does that mean? That just means that x needs to be greater than or equal to 1. Okay, so if I add 1 to both sides here, right, those cancel out, and I have x greater than or equal to 1. Okay, so as long as I have 1 or higher when I plug it in for x, this is going to be okay. We're not going to get any undefined. So this actually tells me what I can write for my domain. So my domain is going to be all the values that are greater than or equal to 1. So the domain, x is an element of the real numbers, and x just has to be greater than or equal to 1. Okay. All right, now let's think about the range for a bit. Well, I'm trying to think about my y values for the range. So what happens is if I follow this rule, if I put anything greater than or equal to 1 in here, then the result of this will always be greater than or equal to 0. Okay, so what do I mean by that? Well, let's plug 1 in. 1 minus 1 is 0, so I have the square root of 0, which is just 0. Okay, if I start to put in things a little bit bigger, like 2, if I put 2 in, then I'm going to have 2 minus 1, and the square root of that is just 1. Okay? So the smallest value I can get for this is actually just 0. So we'll say here the value of the radical is always 0 or greater than 0. Okay? And what that means is the result of this, when I have 0 plus 3, the lowest value I'll ever get for this is 3. Everything else will be higher. Okay. Whenever I square root a number, I'm always going to get a positive. So I'm going to have a positive number plus 3. So that gives me a little bit of insight to this. So I'm actually going to erase the period here, and I'll say the value of the radical is always 0 or greater than 0, and is then added to 3. Okay. So the y values will always be greater than or equal to 3. Okay, how can I write that down now in terms of the range? Well, easily I can just say R for range, and the range has to do with my y values. The y values are an element of the real numbers, and y will always be greater than or equal to 3. Okay, if there was no plus 3 at the end of this equation, it would just be 0 here. Y would always be greater than or equal to 0. Okay, all right, let's just highlight these real quick, those answers. So that's the domain and that's the range. Okay, I'm going to go ahead and enter in that equation. So y is equal to the square root of x minus 1, and then plus 3. Okay, let's move this over and change the size of this a bit. Okay, so I can see here, it kind of looks like a half branch of a parabola, keeps going up and up and up. And it looks like there's a vertex here, and we can see that's at 1, 3. Notice x is not smaller than 1. Okay, x is always greater than or equal to 1, like we had said for the domain. And my y value is my smallest value is 3, and everything is higher than 3. Okay, we will be going over this type of function again and again, and we're going to start to learn how to do their graphs. So for now, I'm going to copy that vertex point, 1, 3, and I'll use that to draw my curve. And this is just a sketch, so it's not like a perfect graph or anything. So there's my y-axis, and then my x-axis here. So 1, 3 would be right here, right? That's 1, and this is 3. And then this curve goes through like that. Okay, I'm just going to label it y equals square root x minus 1 plus 3. So we can see here for the domain, just to go over this again, all my x values have to be greater than or equal to 1. Okay, so 1 is right here. All my x values that are in this curve are from 1 onwards, right? We can see that because this graph keeps extending this way, so I'm going to use everything from here onwards for x. The y values, this has to do with the range. Okay, my output for this function, because this is going this way and extending out, I'm going to use every y value from here onwards and up. Okay. Yes, this graph does grow faster horizontally than it does vertically because it's a square root function, but it's still going to keep going upwards to infinity. Okay, one other thing too, when I'm writing out the domain and range and I use these inequality symbols, okay, I tend to always write them the same way because I always put x first and then I put my number here. So they kind of always seem to fall this way. And if you have a little bit of a hard time with inequalities, something you can always think of, when I read this, I say x is greater than or equal to 1. And if you think of this as like a little alligator or a little Pac-Man, the mouth is open towards the x because um, you can think of it as maybe it thinks the x is bigger, okay, and it wants a bigger meal. So the way how this mouth opens shows you which one is bigger. So when I read this, I can say x is greater than or equal to 1. This is the equal to part for that line underneath there. Okay, if I didn't want to include 1 for some reason, if I couldn't include that, I would just write x greater than 1. Okay, but in this case, we do want to include it, so we leave that part in there. Okay, looking at our last graph, okay, for this example. So I know this has been a little bit of a hefty lesson. There's a lot of graphs here. This is the last one. Okay, and this one here is special. It is a circle. Okay, you might not have seen this in grade 10 or not, depending, but circles always have this form. X squared plus y squared equals r squared, where r is the radius of the circle. Okay, and when it's in this form, it'll always be centered at the origin. So I can see here that if I take this number 36 and I write it as a number squared, it should actually look like 6 squared. So I can see that the radius is 6 for this graph. Okay, graphing these on a graphing calculator can be a little bit tricky. Okay. So I will bring it up on Desmos anyway, but your graphing calculator might have a hard time doing this one because x is squared and the y is squared as well. All right, so my origin is right here in the middle, and I got to draw a circle with a radius of 6. So 1, 2, 3, 4, 5, 6. And then going up, 1, 2, 3, 4, 5, 6 up here. Same thing over here. And then same thing down. Okay. Okay, I'll draw this in red. Now you guys get to see my nice circle drawing capabilities. So it's probably going to look more like an ellipse because the grid isn't exactly square. So if it was a square grid, erase that. Okay, it's kind of terrible looking, I'm not going to lie. All right, that side looks okay. It almost looks like I miscounted here. 1, 2, 3, 4, 5, 6. Okay. Anyway, it is what it is. All right. So that would be my circle. So the domain for this, all my x values that are used, well, my x values range from -6 to 6. Okay, I only use those in here from there to there. Nothing outside of that. So we can say the domain, x is an element of the real number system, and x goes from -6 to 6. So what I do is I actually write this in the same order that you see it on the graph. I write this number first and then that number after, and I sandwich x in between. When I do it like that, I can write the inequalities the same way, and I can say x is greater than and equal to -6, and smaller than and equal to 6. Okay, so notice the symbols go the same way. But if you notice, it's done in a way where I can say this mouth is open towards the x, meaning it's bigger than -6. And this mouth is open towards the 6, meaning the x is smaller than +6. So it's allowing me to go from here to here on the graph. Okay, I always write these in descending order, and I put x in the middle, and then the symbols just go the same way every time. Okay, you'll see that when we go to do the range next. So the range, we'll switch colors, and it's from -6 down there to +6 up there. So the range, this is my set of y values that are an element of the real number system. And my smallest value for y is -6. And the largest value is +6.